Hi, welcome to the video lecture series on CFG context-free grammars. Today we will see a CFG for generating a strings of balanced parentheses. What do you mean by balanced parentheses? It's like when you are writing any arithmetic expressions, it's like a plus b. You have a balanced parenthesis here. So for such balanced parentheses, you have to write a context-free grammar that always accepts a balanced parenthesis. So now what we do, we'll take three type of parentheses, that is common brackets, square brackets and flower brackets. I've taken two examples here. This is one set of balanced parentheses and this is the other type of balanced parentheses. You can see here these two ends at the same time, these two ends at the same time and these two ends at the same time. Suppose if I write this as something like this, then it should get rejected because it is not balancing. So now the grammar for balanced parenthesis is the one that I have highlighted, where you can see first one what you have. If you take only s, if you take only s, you will get its equal in production, that is as shown in the first production. Here suppose if I take the value of s as epsilon, what do you get? You will get the balanced parenthesis like this. Suppose if I take s tends to, if I replace the value of s with this production, what do I get here? S. Now again if I replace s with the first production, I will be getting now if you replace s with epsilon, that is the last production, what do I get? I will get this string which is same as the first string. Okay. Now let us check the second derivation. What I have here, I'll use the production s tends to ss. S tends to ss. For the first s, I'll take the first definition, and for the second s, I'll take the first definition. Actually that should be done in the next step because every time we are replacing only one variable. Next what I do, for the first s I'll take epsilon, second s I'll take epsilon, then the string left out will be this, which is your second string. So the concept is very simple. Whatever the brackets you have selected, so in every production you have to use that bracket with an s in it, where s is a variable which is used for repetition for getting the different combination of brackets, and finally we will end with an epsilon where you need to stop it. So the terminating symbol here we have is the brackets followed by epsilon. Non-terminating symbol or variable is s. Starting symbol is also s only. And the productions, these are the productions you have in the given problem. So this is the problem for balancing the brackets. Next we will move on to the given language, that is obtain the grammar to generate a given language L is equal to a power n b power n minus 3 where n is greater than or equal to 3. Now see what it says is you can write any string, but in that string the number of a's you have should be number of b's, but there should be 3 less number of b's in it. For example, suppose if I have 4 a's, there will be 3 b's, 5 a's, 2 b's, and so on. So in a string, 3 a's should be more compared to the number of b's. Now he is clearly saying that the number of a's, the value of n is 3. Let us consider if the value of n is equal to 3 only, then you will get a power 3, b power 0, that is this string will be 0. So you will get only 3a's. If the value of n is equal to 3, 3a's. If the value of n is 4, you will get 4a's followed by a b. If the value of n is equal to 5, 5a's followed by 2b, and so on. So now what is the basic string? We have got 3a's. So we will take the production s tends to 3a's. These 3a's is taken as it is, and I have taken a variable a which is used for generating these things that I am highlighting, that is more number of a's, or in this case it is epsilon. So the other a can be defined as epsilon, right? So if I want more combinations, no, what I do, I will go for the first half, that is a b. See here, I have already got 3 a's. To generate this, what I can do, I will take a b here, then for a I will take epsilon. Okay, let us see a derivation for it. If I want to get only 3 a's, what I do, I will use the first production s tends to a capital A, and here for this a I will take epsilon. I will take this epsilon, so I will get only 3a's. This we have already got now. Let us go for the second derivation. What we do here, s tends to a is the first production you have got. Now what we do, we will write the first 3a's as it is. For this capital A, I will take the first production, that is a capital A B. See, this is for a power n, b power n, if you remember. You will get equal number of a's followed by equal number of b's, where a can be replaced with epsilon later when you are ending it. So I am using that production in this, that's it. I have added the first production to get 3 extra a's. Okay. Now how many a's we have here? 1, 2, 3, 4, 5. Okay. Now I have to replace this a with b again. So what I do, I'll take 4 a's. I'll take a capital A b b. So this variable next time I'll replace with epsilon. So a 4 a's, one more a. This is replaced with epsilon. Next what we have? BB. This is the string that we have obtained. So this is the grammar we have for getting a power n, b power n minus 3, where v, t, p, s, start symbol is s, two productions we have, terminal symbols are a, b, epsilon, variables are s comma a. So this is the grammar for a power n, b power n minus 3, where n greater than or equal to 3. So we'll go to the next topic, which says obtain a grammar to generate arithmetic expression using the operators plus, minus, star, division and this power. Now see here, these two we have already seen in the past. This is the production to give sum operation. This is the production to give subtraction, multiplication, division and so on. So what we do for every operator, see, every operator should have, every binary operator should have at least two identifiers. So this e, that is the variable, should be finally replaced with an identifier. So that's why we have written e can also take id. So let us try to generate id plus id star id, this using this set of productions. We have to get this string or arithmetic expression using this set of productions. So what we do, we take the first production, e tends to e plus e, first production. Next what I do, I'll be using leftmost derivation, where this e will be replaced with id plus this e, I'll keep it as it is for time being. Next what I do, I'll take it as id plus this e will be replaced with e into e, this production. So I'll get e star e. Next what I do, I'll take it as id plus this will be id star e. Next what we do, we'll replace id plus id. This e what I have, I'll replace with identifier. So you are getting this arithmetic expression. Let me take one more. Suppose if we take id plus id plus id, 3 times I am performing sum operation. So it looks like e tends to e plus e, leftmost derivation, this I will make it as id plus e. Next what I do, e plus e, this I have replaced. So this will be finally id plus id plus id. So finally we have got this string. So using these productions you can get any arithmetic operation. So next we will go for a new topic, that is a derivation tree, so which is also called as a parse tree. So what do you mean by derivation tree? In general, for a given grammar, you will do some derivation, and for the derivation that you have done, you can write a tree for it. So this tree, we will call it as a derivation tree. But the question is how to write it. Okay, see, first we will see the points, then we will see an example. See here, the point says, for a given grammar having VTPS, the derivation tree can be obtained by using the following properties. What are the following properties? See, the start state should be root. That is what your first condition says. Root should be the start symbol, the root should be the start symbol. Next, every vertex has to be labeled with VT. See, V variables union terminating symbols union epsilon. So what this says is every vertex, see this is a vertex, this is a vertex, this is another vertex, this is another vertex. So all the nodes or vertices you have should be from either variables, or it should be from terminating symbols, or it should be epsilon. See, in this vertex is a variable, this vertex is a terminating symbol, this vertex is a variable, this vertex is a terminating symbol. Likewise, every vertex or every node should be either a variable or a terminating symbol or an epsilon. Now, every leaf node should be terminating symbol. See, leaf node, terminating symbol, leaf node, terminating symbol, leaf node, leaf node, leaf node, leaf node. All the leaf nodes should be a terminating symbol, and every intermediate node should be variable. See, an intermediate node, variable, an intermediate node, variable. So these are the conditions we should know. What are the conditions? Root should be the start symbol. Every node should be either it should be from V, or it should be from T, or it should be epsilon. Second condition. And the third condition is leaf nodes should be terminating symbols. You can see here all the leaf nodes, and all the leaf nodes should be terminating symbol, and all the intermediate nodes should be non-terminating symbols or set of variables. Now see here how to write the derivation tree. Let us take a simple grammar. S tends to AB, S tends to AB or ASB. So what I do, I will take the first production as S tends to ASB. So for this S, again I will take ASB. For this S, you can see here I have taken the second production only, that is ASB, and for this S again I am taking AB. So what is the string you obtain from here? You will get 3 A's followed by 3 B's. That is, the language generated by this is A power n, B power n, okay, where n is greater than or equal to 1. How to write its equivalent derivation tree? The start symbol is S, so we have taken S. Now, in the first derivation, see, S tends to ASB. So, S is defined as ASB. S is defined as ASB. In the second production, what I did, S I replaced with ASB again. See, S I am replacing with A, S, B again. Now in the third time, again the S is replaced with AB. Third time, S is replaced with AB. So this is the derivation tree, you get it. Suppose if I write one more derivation like this, S tends to ASB, this I'll write it as ASB again, this is B as it is. Next time if I take this S as AB, you'll get 3A, 3B's, no? Like see, ASB, you started with S, ASB, ASB. Second, what you did, the value of S you replaced with ASB again. S is replaced with ASB. Now S is replaced with AB, so S is replaced with AB. Further, you cannot derive because you don't have any non-terminating symbol here. So it's very simple. Writing a derivation tree or a parse tree based on the derivations that you have got for a given grammar. That's why we call it as a derivation tree. So we'll take an example here. See, I have taken a grammar from here, the grammar that you have seen before, to generate the arithmetic expression. See, this grammar I have considered. What I am doing here is E tends to E plus E, that is the first production, where E I have taken it as ID. This E I am keeping it as it is. Next, ID I have taken, and this E is replaced with E into E. E is replaced with E into E. Then what I do, the leftmost E I will replace it with ID, and rightmost I will keep it as it is. In the next step, I will replace this ID also. So we have done the leftmost derivation that we have seen in the example. So for this, its equivalent derivation tree will be, say, look at the string that I have got, ID plus ID into ID. Let us see its equivalent derivation tree. E is defined as E plus E. E is initially defined as E plus E. Then E is replaced with ID. So leftmost E is replaced with ID, right? Then this E is replaced with E into E. This E is replaced with E into E. Then this E is replaced with ID. This E is replaced with ID, and this E is replaced with ID. Now see here, root node is a starting symbol. Intermediate nodes are non-terminating. Leaf nodes are terminating. ID plus ID star ID. So this is what the derivation tree we get for leftmost derivation. Let us see the rightmost derivation for it. So what I do here, this E I will keep it as it is, but the rightmost E I will replace it with E into E. See, I have E. E is replaced with what? E plus E. E is replaced with E plus E. And this E, what I had, this E, I am taking it as E into E. This E, I am taking it as E into E. And the rightmost E I am replacing to ID. Then next rightmost I am replacing it to ID. And the last rightmost I am replacing it to ID. So the string you are getting from here is ID plus ID into ID. These two are same. And look at here, this is leftmost derivation and this is rightmost derivation, but their derivation trees are same. That is the note you should know here. Leftmost derivation tree is equal to rightmost derivation tree. So this is another type, two types of derivations that we have already discussed in the previous classes, leftmost derivation and rightmost derivation, and we know that we got to know that their derivation trees are same. So we'll go for the next topic, that is ambiguous grammar. So what do you mean by ambiguous grammar? The grammar is said to be ambiguous if there exist multiple parse trees. What do you mean by parse trees? That is nothing but derivation tree only. A grammar is said to be ambiguous if there exist multiple parse tree or derivation tree for a given string. Look at this. I have taken a grammar, E tends to E plus E, E tends to E star E, E tends to ID. That is the grammar which is capable of performing sum or multiplication. So the string I am obtaining here is ID plus ID star ID, and the tree we got to know in the last example. We already know how to write this tree. But now here the same thing can be obtained in the other way also. What I am doing here, you have E star E. See here, I am considering the first production to get it. E tends to E plus E. I started with the first production. Later I replaced the second E to E star E. I started with the first production, and in the further production I am using the second production. But you can see here I am directly starting with the second production and gradually I am using the first production in it. See here, finally, whatever the string you are getting in both the examples are same. And I am using this grammar only to get the strings. But their derivation trees are different when you are using such productions. See? Hence we say it is ambiguous. Okay, if you want, I'll just show you how we got it. What I am doing here is I am using the first production. Here I am starting with the second production. See here, this will be ID plus E, ID plus E star E. This will be ID plus ID star E, ID plus ID star ID. If you use this, you will get this tree. Suppose if you use this, if you start with the second production, it will be this will be ID plus E star E, ID plus ID star E, then you have ID plus ID star ID. For this, you will be getting this production, that is, you are starting with E, the next symbol you take is E star E, then this E you will replace it to E plus E, this E you are replacing it with E plus E, and then you are changing it. So, for the same grammar, to obtain the same string, for the same grammar, to get the same string, if you are getting multiple parse trees or derivation trees or different derivation trees, we will call it as ambiguous grammar. We will see one more example for this. Okay, see here, the question will be like this: is the following grammar ambiguous? They will give the grammar to you. You have to check whether if it is ambiguous. So now what I do, I will take two derivations, that is derivation 1 and derivation 2, to get the string, that is 4 A's I want to obtain. So here what I do, I will start with S and I will use this production, that is S tends to AS. Now I have to get 4 A's now. So what I do, this S I will replace with double A in the next production, and this S I will replace it with X. This is not there. See, S can be X also. So yes, I am replacing with X. Next what I do, I will take 2 A's. This X can be replaced with AX, no? So this X, I am replacing it with AX. So finally this X, I am replacing it with A. So for this, if you write the derivation tree, it looks like this. You have AS, then that S is replaced with X, then you are writing A. So this is a derivation tree for the above one. Now this is one case of getting 4 A's. Instead of taking AS for S, I can take X also. So S tends to X, where X can be AX, and again X can be AX, X can be AX, then X can be A. I am not using AS at all. With X only I am deriving all the 4 A's. So its derivation tree will be different here. Here you are defined with S, X. In this you are taking only X in all the derivations. So the string obtained here is 4 A's. Here also the string is obtained is 4 A's by using the same grammar. But you have two different derivation trees. Hence we say it is ambiguous. So let us see the next problem. Is the following grammar ambiguous? And the grammar given is S tends to ASB, SS, epsilon. So see, ASB, that means what? If I keep on taking the value of S as a repetition symbol, I'll be getting n number of A's and n number of B's, right? So let us derive a string AA. Here I have taken the definition of S as ASB, and here for S, here for this S, I'm taking its equivalent definition as SS. So its equivalent definition is SS. So next what I do, for this S, that is the first S, I'm taking ASB again. So first S will be ASB. Second S I have kept it as it is. You can see here. Second S I have kept it as it is, and B is also as it is. In the next definition of the production, what I do, this S will be replaced with epsilon. So here you don't see that S, and this S in the next production will be replaced with epsilon. So you will get AABB. If I write the derivation tree for this, what I did, first I have taken S tends to ASB, S tends to ASB. Next what I did, in this S was replaced with double S. So S is replaced with double S using the second production. And after that what I did, the first S what you have here was replaced with ASB. First S is replaced with ASB. Second S I replaced with epsilon, the last definition. In the next step I replaced this S with epsilon. Now look at the string in the leaf nodes. AABB. AABB is the string obtained. This is one type of derivation tree we have got here. Let us see the second derivation. Here we started with ASB, but here let us start with SS. So S tends to SS, where what I do, the value of this S I'll replace with epsilon. So you will get only S, right? S tends to S. Next what I do, S can be replaced with ASB. Then this S can be replaced with double S, where what I am doing, here you can see first S I replaced with double ASB, second was epsilon, but here I am doing the reverse of it. First S I am replacing it with epsilon, second one I am replacing with ASB. So obviously when I reach AABB, the derivation tree that I get for this is different from the derivation tree that I have got here. So we say it is ambiguous. So the string I am obtaining here is AA only, but the way of obtaining is different, and we have multiple derivation trees. Similarly, if you try in different way, you may get even more derivation trees. That's why we say the given grammar is ambiguous. Okay, we'll stop here and we'll see some more examples in the next class. Thank you.